All right, so one of the things that we did in pre-calc was you would take a look at a graph, right? You would take a look at a graph, maybe something that looked like this, and you would be asked, based on the graph, to determine where the function is increasing and decreasing, where relative maximum and minimum points are. Yes,
That's
that's true.
like
They are.
the end behavior.
I'm having trouble hearing you, Josh.
Oh yeah, yeah, that kind of sounds like determining the end behavior.
Yeah, yeah, but that's not yet. Sort of, yes, but not quite where I'm going with this. But yes, that was one of the things that we had to do. But what I'm particularly interested in is where the function is increasing and decreasing, and where the function hits relative maximum and minimum points. All right, so in pre-calc, you would have looked at the graph and you would have used a calculator to estimate things like where is the function where is the function going up, where is it going down, like that. Where does it hit a maximum point or a minimum point? All right, but now that we can calculate the derivative and we have some background and some meaning to put to what the derivative is, we can do this algebraically and get more than just estimates, get exact values. Right? So where I want to start here is with the I'm trying to think of with the definitions. All right, like official like definitions of where a function is increasing and decreasing and how you determine that. All right, so I'm going to use this as my example function. So I'm going to call this y equals f of x. All right, so if I impose an xy axis on this, so I'll just do this. All right, and let's say I take an interval from A to B like that. All right, so that translates up here to f of A and f of B. All right, and I look at the open interval here from A to B. All right, so that is the open interval on the function from here to here. Now, if I examine that, I can see that that part of the function is going up. All right, so I can see that between A and B, my function is increasing. So to put a definition on this, okay, let me hang on, where's my mouse? I just want to make sure I'm not writing behind myself. To put a definition on this, all right, we say that a function f is increasing on an open interval from A to B if for every x in the interval from A to B, f of x, f of A to B. Okay, so then I'm going to put a couple of x's in here, right? x1 and x2. Should have made my interval bigger. F of x2 is greater than f of x1 when x2 is greater than x1. All right, so basically, as x increases, the function increases. Right? I can make a similar definition over here. If I take another interval over here, all right, let's take that one out. Call this one AB now, and an x1 and an x2. Because I'm now on this side of the function, right, this now becomes f of a, this now becomes f of b. So when I put the x's in there. All right, so when I take x1 and x2 this way, all right, the roles of f of a and f of b reverse. All right, so f is decreasing on an open interval from a to b if for every x in that interval, f of x1 is greater than f of x2 when x2 is greater than x1. All right, so again, as x increases, the values of f of x decrease. All right, now this was basically the definition that we used in pre-calculus. Okay, this was our visual function definition for a function being increasing or decreasing. All right, so what I want to do now is I want to extend that to the calculus that we have figured out at this point. All right, and the calculus that we figured out at this point has to do with the first derivative. Right, so the first derivative, right, f prime represents, I'm just going to say equals the slope of the tangent line to the curve. Hang on one second. No, because we always talk about x increasing. All right, so you always start at x1 and move to x2, which means x2 is always greater than x1. All right, so you always move x in this direction. The function could go up or down, but x always moves to the right. So x2 is always greater than x1 when you're talking about a function being increasing or decreasing. Okay. No problem. That's a confusing point for almost everybody. All right, so f represents the slope of the tangent line to the curve. So the tangent line to the curve on this side, right, in this interval here, is, if I take a point, is going to have a positive slope. All right, so if f is increasing, the slope of the tangent line to the curve is going to be positive. All right, then f prime is going to be greater than 0. And if I look over here on this side where I could see that my function is decreasing, and I put a tangent line in on that side, any tangent line on that side is going to be decreasing, have a negative slope. So if, over here, if f is decreasing, then f prime is going to be negative, less than 0. All right, so that's all based on the slope of the tangent line to the curve. So, all right, so that's our kind of visual definition there. All right, so let's make this formal. All right, so what I want to do to make this formal is this. We get a theorem here, and our theorem has 3 parts to it. First part is if f prime of x is greater than 0 for every value in the interval from a to b, right? It's greater than 0 for every x in an open interval from A to B, all right, then f is increasing on that open interval. All right, so if you take the derivative and you look at where that derivative is positive, anywhere where that derivative is positive, the function is increasing. All right, the second part of this is, well, if f prime of x is less than 0 for every x in the open interval from A to B, then f is decreasing on AB. So if your derivative is negative, then your function is decreasing. Now there's one extra part that the book puts in, and that is if f prime is 0 for every value of x in an interval, then f is a constant function. All right, so I'll put that in. All right, so if f prime of x equals 0 for every x in an open interval AB, then f is constant on AB. Now, we have to be a little careful here, and I sometimes hesitate to put this last one in, because f prime of x can be 0 for a single value. All right, that's fine. This last condition is only if it is 0 for any value in the interval. That means you're dealing with a constant function. Okay. So if I want to, let's take a function that we know. All right, let's take f of x equals x squared. All right. So if I can't find my mouse again, I hate when this happens. Okay, this is, hang on. Seriously, there it is. Okay. I have way too much screen real estate. I keep losing my cursor. All right, so if, that's because I want to do that. All right, so let's take the function f of x equals x squared, right? We know what that looks like. I want to find the intervals where f is increasing and decreasing. All right, so that means, all right, another way of saying that, so I'll put that down here in parentheses, is where is f prime greater than 0 or f prime is less than 0. Okay. So the first thing I need is f prime, right? F prime of x, derivative of x squared is 2x. All right, so I want to know where 2x is positive or negative. All right, so one thing that's going to help me there is to find out where it's 0. Right, so this is equal to 0 at x equals 0. And if I do a sign line, remember the sign lines from pre-calc? Right? If I do a sign line for the derivative, then I could put test points in here, but I think that's kind of silly at this point, right? 2x is going to be positive on this side and negative on this side. Now we use this technique in pre-calc with the function to determine where the function was above and below the x-axis. With the derivative, right, finding where the derivative is positive or negative, about the function means where is it increasing or decreasing. So where the first derivative is positive over here, I know my function is increasing. I'm going to write it out in a minute. And where my first derivative is negative over here, I know my function is decreasing. All right, so f is increasing on the open interval from 0 to infinity. And f is decreasing on the open interval from negative infinity to 0. All right, so that's very similar to what we did with functions when we were solving inequalities, right? Or trying to graph, find out where something is positive or negative. It's the same idea, only now we're doing it with the first derivative, which gives it a slightly different meaning. Okay. All right. Okay, so now to determine the intervals where a function is increasing or decreasing, you're going to find all the values for which the first derivative is 0 first, and then you're going to do a sign pattern, okay? So I'm just going to grab something out of the book here because I don't feel like writing all that down. Hang on one second. Let me do this. No, we did not. And I'll repeat what I said again at the end. Okay. All right, so here is our process. All right, here's our process. Right? You determine, all right, what are called the critical numbers. So the critical numbers for a function are anywhere where the first derivative is 0 or the first derivative is discontinuous, where it's not defined. All right, so let me throw that in up here. All right, so we can define the words critical numbers. Sometimes critical values. I tend to say critical values, but the book says critical numbers. So that's what I'll write. But if you hear me say critical values, same difference. All right, so critical numbers are any values, any x values, where f prime is equal to 0 or f prime is not defined. All right, so when you are trying to determine where a function is increasing or decreasing, first determine all the critical numbers for the function. Determine the sign of f prime, do a sign line, right? Determine the sign of f prime to the left and to the right of each critical number. All right, if f prime changes sign from positive to negative as we move across the critical number, then f has a relative minimum at that critical number. So if you go, I'm sorry, relative maximum at that critical number. So if you go from positive to negative, right, increasing to decreasing, you're hitting a maximum. You go up, you hit that maximum, you come back down again. So your function is increasing and then it's decreasing. So your first derivative is positive and then it's negative. All right. If f prime changes from negative to positive as you move across the critical number, then f has a relative minimum. So go the other way, right? If you go from negative to positive, right, from decreasing to increasing, You go down, you hit a minimum, you go back up again. So the first derivative is negative going down, positive going back up. Right? Now, if f prime doesn't change sign as we move across a critical number, then f does not have a relative extreme point, right? There is no relative maximum or relative minimum. Now, that is absolutely possible, okay? Now, when you're dealing with polynomials, right, it is possible, even with a polynomial, to have a situation where you don't change signs, okay? Now, I'm going to go through an example. Come on, move. Okay. I think I've got a couple of things running in the background right now. Let's take a look at this. So f of x equals x to the third minus 3x squared minus 24x plus 32. All right, so the polynomial, we'll take a look at what it looks like in a couple minutes. But I want to determine where the function is increasing and decreasing. All right, and then we're going to use that information to determine for the critical point, for the critical values that we find, where we have a maximum or a minimum point. Okay, so we take the first derivative. So that becomes 3x squared minus 6x minus 24. All right, so I have to set this equal to 0 and solve it. So the first thing I'm going to do is I notice I have a factor of 3 running through this entire problem. So I'm just going to divide that out. So I'm going to get x squared minus 2x minus 8. And then when I divide 0 by 3, I still have 0. All right. And then this will factor, right? This is going to be, all right, let's see, 8 would be 4 and 2. That'll give me 2, and I need a negative 2, so that means I need an x minus 4 and an x plus 2. Again, use whatever method you want to solve it. If you want to use the quadratic formula, go ahead, that's fine. So this one is going to give me an x equals 4, right? Because 4 minus 4 is 0. This one's going to give me an x equals negative 2. So negative 2 plus 2 is 0. Right. So I have 2 critical values here. All right, now I'm going to use the factored form of the derivative to determine my sign pattern, right? Because dividing, but that 3 is not going to change the sign pattern. Okay, so, all right, so 0. Let's take 0. All right, so my derivative is 0 here and 0 here. All right, this is f prime that we're looking at. All right, so if I put 0 in here, I get a negative 4. If I put 0 in here, I get a positive 2. That means I'm negative in that interval. And again, all this goes back to that technique we learned in pre-calc. All right, so everything's working the way it is for the exact same reason it did there. All right, so take something on this side, so maybe like negative 3, something in that interval. So if I put negative 3 in here, I'm going to get a negative 7. If I put negative 3 in here, I'm going to get negative 1. All right, which means I've got a negative times a negative, which means this is positive. And if I take something out here, maybe like 5, 5 minus 4 is 1, so that's positive. 5 plus 2 is 7, so that's positive. I don't care what the number is. I just care that I'm multiplying a positive by a positive. All right, so now I have the sign pattern for my derivative. All right, so where the derivative is positive, the function is increasing. All right, so f, I have to mark on my screen where my little insert is. Didn't get to do that yet. Okay, so f is increasing. All right, well, f is increasing where the first derivative is positive. So that's on the ends here. So that is from negative infinity up to, but not including negative 2, because at negative 2 it's 0. And then also from 4, but not including 4, because at 4 it's 0, to positive infinity. All right, so that's where the function's increasing. F is decreasing anywhere the first derivative is negative. So that's in between these two. So that is between negative 2 and 4. Okay. All right, so I have a rough idea of the shape of this. Now let's talk about these critical values for a minute, right? Because those critical values are where possible relative extreme points could occur. So if I go back to what I had written up top where you can't see anymore on the board, if the function changes from increasing to decreasing, so think about that. The function is going up here and it's going down here. All right, so if it goes up and then down, this point has to be a maximum. That has to occur at a top point. So x equals 2, negative 2, x equals negative 2 is a relative maximum. Nice, I'll write it out. All right, so over here at 4, again, another critical value. The function is decreasing, negative, and then increasing, positive. So when you go from decreasing to increasing, you hit a point at the bottom. So that is a minimum point. So x equals 4 is a relative minimum. Now, it's not the minimum value of the function or the relative minimum value. It's where that value occurs, right? So technically, x equals negative 2 is where the relative maximum occurs, and x equals 4 is where the relative minimum occurs. To find the actual value of the maximum minimum point, you would have to plug those numbers back into the function, right? But for right now, I'm just interested in the x values. Make sure you can find them. All right. Now, if we take a look at what the function looks like, all right, I already have a rough idea of the shape, right? I know that this function is going to go this way, right? It increases, it turns around, it decreases, turns around again, and it increases. So it's going to have a shape that looks something like that. All right, but the details, it's all in the details. So, you know what? I'm just gonna, let me do this. I'm like, do I want to go over to GeoGebra? But I think I'm just gonna grab the image from the book, and we will go with that. Okay. Copy, there we go. All right, so let's take a look at what this looks like. I'll put it over here. All right, so here is the actual graph. All right, so one of the things you can see here is if I wanted to actually graph this without going to my calculator, I could with the information I have here. I actually have enough information to get a reasonable picture of this graph because you can see where the maximum and minimums occur, right? I can't see. All right, so the maximum, show my cursor, there we go. All right, so the maximum occurs up here, and that looks like it's right around 60. And the minimum occurs down here, and that's somewhere down here. They don't put a point value on it. all right, but it might be right around 50. All right, so you could find those values exactly by taking your your critical values and plugging them back into the function. All right, so I can find those maximum minimum values now without having to resort to a calculator. Okay, well, without having to resort to a grapher. And I'll get exact values, not estimates, which is also nice. All right. Okay, so what else can we do with this? All right, how about I said, all right, so when I defined the critical value, I said it's anywhere where the first derivative is 0 or the first derivative is undefined. All right, so let's take a look at another function here. Let's take a look at f of x equals x to the 2/3. Okay. All right. Now with this function, all right, so the domain of this function is all real numbers, right? There's nothing in there that's going to restrict the domain of the function. So I don't have to worry about any points where the function is not defined or the function is discontinuous. It's continuous everywhere. The derivative, if I take f prime of x, this becomes 2/3 x to the negative 1/3. Right, so this is 2 over 3x to the 1/3. So there is no place where the derivative is 0, right? Because again, a fraction is 0 where its numerator is 0. And the numerator of that fraction will never be 0. But there is absolutely, oh, okay, sorry. There is absolutely a place where the derivative is not defined, right? If x is 0, then the derivative is not defined because that would put a 0 in the denominator. All right, so x equals 0, I should say 4, x equals 0, f prime of x is not defined. It has a discontinuity there. Not the function, but the derivative. All right, but x equals 0 is still a critical value. All right, so when I want to find where this function is increasing and decreasing, all right, I am still going to use that to figure that out. All right, so if I put a positive value in for x into the derivative, I'm going to get a positive value out, right? If I put 1 in there, I'm going to get 2/3. That's positive. So on this side, the derivative is positive. And if I put a negative value in here, because that's an odd root, I'm going to get a negative value out. So if I throw a negative 1 in there, I'm going to get negative 2/3, which makes this side negative. All right, so f of x equal, okay. You know what? Give me a second. I need to turn that. I need to turn that feature off. I'm getting tired of getting triangles when I write stuff. Hang on. Where is it? To shape off. Okay. All right. So f of x. That is f of x. F of x equals x to the 2/3 is decreasing. Let's say on the interval from negative infinity to 0, not including 0, and it is increasing on the interval from 0 to infinity. Again, where the first derivative is positive or negative. All right, now this particular function, all right, we don't have enough information to get the exact shape just from this. All right, but I guess we could, you would have to plot some points, but what this function looks like, this one's easy for me to draw. This basically looks like this. All right, and this point right here, all right, again, back in pre-calc, we called that a cusp, right? That's a sharp point on the graph. And a sharp point on the graph is an undefined tangent. That is what's called a vertical tangent line. So if I were to start drawing tangent lines on here, right, as I come this way, eventually I'm going to get here and the tangent line is going to go fully vertical. And the slope of a vertical line is undefined. It's infinite. So that's why, right? Or that's why the derivative doesn't exist there, right? Because there's a vertical tangent there. All right, how about this? How about this one? Another function with a similar type of issue. All right. Now, when we did x to the 2/3, x to the 2/3 was continuous, right? It was defined everywhere. I can put in positive values, I can put in negative values, I can put in 0. I don't have any issues with that. I do have an issue here, right? This function has a restricted domain, right? Because x can't be 0 here. Essentially, this has a vertical asymptote at x equals 0. All right, so I already know that my function is not defined at that point, which means I can be pretty sure that my derivative is not going to be defined at that point. All right, if I take the derivative of this function, all right, the derivative of x is 1. The derivative of 1 over x, well, that would be x to the negative 1. So that would be negative 1 x to the negative 2. So that would be negative 1 over x squared. Right? And again, this comes from this by looking at that and saying it's x to the negative 1. Right? So the derivative is negative 1 x to the negative 2. Right? And that's how that comes about. Okay. All right. Now, if I want to, so again, I can see right here, right? Here is that point where the derivative is not going to be defined. All right, so I can tell without doing any work to this, right, that x equals 0 is a critical value. Oh, man. Spelling sucks. Okay. Critical value. All right, but there still might be more because there's still the possibility that f of x could equal 0. All right, so the proper way to do this would be to get a common denominator, combine this, and then factor the numerator. You could also set it equal to 0 and cross multiply. If we already know that x can't be 0, all right, then we know we're not multiplying by 0. But I'm actually gonna do it this way. All right, so I multiply 1 by x over x squared over x squared. So I get x squared minus 1 over x squared equals 0. Okay, so x plus 1, x minus 1 over x squared equals 0. So that's going to be where x is equal to 1 or x is equal to negative 1. All right, these are also critical values. All right. All right, so I have a function that has 3 critical values. Let's look at the sign pattern and see if we can determine where this function is increasing and decreasing. Right? And I'm going to use one of the reasons that I wanted to have this factored form for the derivative is I want to be able to use it to get my sign pattern. Right? It's easier to get the sign pattern if you have the factored form for the derivative. All right, so I've got a critical value at 0 where the derivative and the function this time are undefined. I have one over here at -1, and I have another one over here at +1. Both of these are where the derivative is 0. So remember, this is f prime. So I'm looking up here. Make sure I'm looking at the same thing you're looking at. All right, so I am looking up here for my sign pattern. All right, so I'll work my way in. All right, so let's start over here. If I take a value over here in this interval, say I take -2. I put -2 in here, I get a negative. I put -2 in here, I get a negative. Negative times negative is positive. My denominator is always positive because it's being squared. So that means everything is positive. Let me jump over to this end. All right, I'm going to take a value over there, +2. All right, if I put a +2 in here, that's going to be positive. If I put a +2 in here, that's going to be positive. So my numerator is positive. My denominator is always positive. So that means everything in this interval is positive. All right, so now I have to take a point between 0 and -1. So I'm going to take -1/2. So if I put -1/2 in here, that's not going to change the sign here, right? That's going to stay positive. If I put a -1/2 in here, that's going to stay negative. So if a positive times a negative is a negative, the denominator is always positive. So that makes my whole fraction negative. If I take a +1/2 in this interval, all right, 1/2 in here, my first term will stay positive. 1/2 in here, well, 1/2 minus 1 is -1/2, so that's going to be negative. So again, I have a positive times a negative is a negative. The denominator is always positive, so that's going to be negative. All right, so here we have a situation where we have a critical value at 0, but notice that the function doesn't change sign there. All right, so not every critical value is going to be a point where the function changes sign. All right, so that just means it doesn't change from increasing to decreasing there. It just stays decreasing. All right, now what this function looks like, all right, what this function looks like is, hang on one second. Let me just grab it here. All right, so here is what this function looks like. Notice it has a slant asymptote is what it's got. And if you remember from pre-calc, again, I realize I'm asking you guys to think back for some of you a little bit longer than last semester, but if you look at the form that this is, right, and you think about the end behavior of this function, as x goes to infinity, this term goes to 0. And if this term is going to 0, then the function is behaving like f of x equals x, all right, which is how we get this slant asymptote here. All right, but if we look at the behavior of the function based on what I have here, right, the function f, so f is increasing from -infinity to -1, not including, and from 1 to positive infinity, that's an infinity, all right, f is decreasing in between -1 and 1, but not including 0, right, because it's undefined at 0. So when we say it's decreasing in there, it's decreasing from -1 to 0 and from 0 to 1. But notice we're not including 0 there. All right, so the function is increasing right? From negative infinity up to -1, right? There's -1. And then it turns around and it starts decreasing, right? And it decreases all the way to 0, just like we said here. All right, but again, at 0, we have an asymptote. So we have to jump over that asymptote. And on the other side of the asymptote, we're up here now. So we're still decreasing to +1. And then it turns around and starts increasing again. All right, so you get a lot of information about the behavior of the function just by looking at the first derivative, right? And seeing where the first derivative is positive and negative, where the function is increasing and decreasing. All right, let me see. Okay, so I talked about relative extreme points. I kind of want to emphasize here when we talk about relative extreme points, functions can have lots of relative maximum, relative minimum points. All right, it's not just one or one maximum and one minimum, a highest point and a lowest point. That's not actually what we're talking about. Where is it? There it is. That's not actually what we're talking about when we talk about relative maximum minimum points. And again, we went over this in pre-calc, but just to kind of remind you, all right, just to kind of remind you, take a look at this. All right, so this is an example of a function. It's very wiggly, but that's okay. All right, of a function that has several maximum, several minimum points. So anywhere where you have that change from increasing to decreasing, right? You have it here again from increasing to decreasing, is a relative maximum. There's a reason it's called a relative maximum, and that is because you're only looking at a small interval around the critical point to determine whether it's a maximum or a minimum. So it looks like this maximum is occurring at 5, right? So we're making that determination by looking at just this little bit around 5, right? So if I project that back up onto the function, and you take a look at that maximum point up there, that is the highest point in that interval. All right, the same thing is true here for this relative maximum point. This looks like it's occurring at 11. So if I look at a small interval around 11, that corresponds to a small interval on the function like that. And in that small interval around that point is the highest point in that interval. So that's what makes it a relative maximum. All right, the same thing is true for minimums, but in the other direction. So we can write a formal definition of relative maximum and relative minimum in terms of the function. Okay, so the first thing we need is we need a critical value, right? We need that point that we're looking at to be a critical value for the function. All right, so let's do this. So we have a function f. All right, so f has a relative maximum, we'll start there, at the critical value x equals c if there is an open interval around c, so I should say around x equals c, just so you don't get, come on. Ugh, the lag is starting to bug me. Around x equals c, so that f of x is less than or equal to f of c for all x in the interval. All right, so again, the way that corresponds, let me move that there, all right? The way that corresponds is if you, there we go. If you look up here, all right, my critical value is 5, right? I can make an interval around 5 so that for every value in that interval, f of that value is going to be less than f of 5, right? That makes that a relative maximum. I'll cover that up. Okay, so f has a relative minimum. Minimum at the critical value x equals c, again, if there is an open interval all right, no problem. If there is an open interval around x equals c, so that f of x is greater than or equal to f of c for all x in the interval. Okay. All right, and again, same way that corresponds to our minimum value. I can just squeeze it in. I think I can. Yes, I can. All right, so if you take a look at the minimum value here, it looks like our critical value is 11. So I can find an open interval around 11 so that every value in this interval, f of that value is going to be, oh, that's a maximum. Sorry, there's my minimum. I didn't do a minimum. Okay, here we go. 8. All right, so when I put that back on the function, all right, so 8 is our critical value. I can open interval around 8 such that for every value in that interval, f of those values are going to be less or greater than or equal to f of 8. Okay. All right, so that's going to be our working definition for, come on. That's going to be our working definition for relative maximum and relative minimum points. Okay. All right. Let me just see.